Okay, so why do we care about redox? This whole next section is going to be about what redox does for us. And what it does is it powers, it's the process that makes batteries work. And we all love batteries in our devices, right? Like in our phones, even in our cars have batteries, remotes, whatever. So what does that have to do with redox? So you learned about oxidation. Let's say we had some zinc getting oxidized. We did one of those reactions, and we had some copper getting reduced. And we said oxidation is losing electrons, so there go the electrons, and whoever gets reduced gains them. So what you have when you have two metals, one losing, one gaining electrons, is now you have a flow of electrons. And what do you call a flow of electrons? So if you just have electrons going wee all the way from here to here, what do you call a flow of electrons? You call it an electrical current. That's why it's called electricity, because it's made of electrons. So when you have electrons flowing from one metal to another, you have an electrical current. So we don't want to just put the zinc and the copper right next to each other and just let the electrons flow right from one metal to the other. So what we actually do is we separate them. We put one in like this container over here and one in this beaker over here, and then you're like, okay, well, how do electrons flow? We're going to connect them with a wire, and we're going to force whatever's going to happen, that flow of electrons, to happen through the wire. So instead of just letting them be next to each other over here, we're going to say, no, we're going to separate you, connect you with a wire. So now you have to flow your electrons through the wire. So now what do you have when you have electrons flowing through a wire? Well, you have a wire with an electrical current flowing through it. So what can you do with that? You can put something in there. Like you could put a light bulb right here. That doesn't really look like a light bulb at all, especially because the top got cut off. Wow, that's really bad. It was supposed to be like, the bottom part. So you can put some electronic in there and charge it, because you've now got electrons flowing through a wire from something being oxidized to something being reduced. We could put a cell phone in there. There's a phone. We could put like a little voltmeter in there and just have it like, it's like this little dial, and it goes like this to tell us how many volts of electricity we're getting. All right, so that's why we care about redox. That's why we're doing this second part of the unit, and it is called electrochemistry. It's electrochemical cells. So it's electricity, electro, from chemistry, out of little cells. These are spontaneous reactions because we want your battery in your phone to work spontaneously. You don't want to have it always plugged into a power source. So you want a spontaneous reaction. You want your phone, your battery in your phone, to just spontaneously give off electricity without needing to plug it in. And we do call these cells voltaic. You might hear the word volt in there because they do provide volts of electrical current. So again, we use a redox reaction. Electrons are exchanged from what's oxidized to what's reduced. We have two different types. The first we're going to talk about is voltaic cells. And what they do is they take chemicals and turn it into electricity for us. We are going to talk about a different cell that goes the other way, electrical to chemical. And you need to know this one. And the way I remember it is, okay, so a voltaic cell is a battery. And what would you want a battery to do? Do you want it to do you want to plug it in, take electrical energy, and turn it into chemicals to do chemistry? No. You want chemicals inside the battery of your phone. Like if you've ever heard phone batteries are actually really toxic to dispose of because they're full of chemicals. Okay. So they're full of chemicals that are going to give us electrical energy. They're going to take chemical energy and convert it to electrical. And whenever it starts to run out, we're going to plug it back in and recharge it and get more chemical energy to turn into electrical. Okay, so you have to know chemical turns into electrical. All right, so let's build a battery. We're going to build it out of zinc right here, and copper right here. And that's what the guy used in Breaking Bad when they were out in their little meth trailer in the desert and the battery to the car died. He took some zinc, screws or washers or something, and copper, and he built a battery. Okay, so let's build a battery. So you need a zinc, you need zinc and a copper. So the zinc will get oxidized and the copper will get reduced. And oxidation is loss, so this must be losing electrons. Reduction is gain, so this must be gaining the electrons. So there you go. You have one losing, one gaining, so that means you have a flow of electrons. So what do you put it through? You put it through a wire. So then you can put a device right here that you want to power. So we call the end that gets where your reduction occurs, we call that the cathode. So this is the cathode over here. So reduction happens at the cathode, so we remember it, red cat. It is the positive one, and a lot of people remember that either like the T in cathode looks like a plus sign, or if you like cats. I think we talked about this before with cat ions are positive, so we said, okay, cat, if you like cats, then they're a positive thing. So either way, the red cat is the positive end. And it's the one that's gaining electrons. The electrons are spontaneously flowing to it because reduction is gain. So it really helps if you know all these little memory tricks because you're going to have to use them all. Then the other end is the anode. And so you can remember anox, like you know how you can't say ox, you have to say anox, so you put like an in front of where the vowel. So anyways, it's red cat and anox, so you're like, oh, this is where oxidation occurs, it must be the anode. It is also the negative electrode. I can remember that because just like anion was the negative one because there's an N in it, or because like the antagonist in a story is the negative one. But however you remember it, you have to remember that that's the anode. So you have to look over here. You would look at, remember zinc, you would have to go, oh, its charge went up, so this must have gotten oxidized. So you're going to use those skills from before to go, oh, charge went up, so it got oxidized. You go, okay, oxidation is lost, so it must be losing electrons. Anox, so this must be the anode. Anode is negative. So you're using all these memory tricks. Just from these memory tricks, you figured out that this is getting oxidized, that it's losing electrons. The electrons are flowing this way. It's the anode, and it's negative. So you really want to remember all these little tricks. And then the cathode, I knew it was reduced because I'm not doing it now, but in the last video, or I don't know, last video, we went, oh, the charge went down. So I guess it got reduced down. Okay. So we're not doing that now, but we learned it before. So you go, oh, this is the site of reduction. The copper is the reduction one. Red cat. Okay, it's the cathode. Cats are good. Okay, it's the positive one. Reduction is gain. Okay, I guess the electrons flow this way, gains electrons. All right, so once you figure out one of these things, once you figured out this is the cathode, you know it's reduction, it's gaining, it's positive. Or once you figure out it's reduction, you know it's gaining, it's the cathode, it's positive. Okay, so once you figure out one of these things, you should know all the other things about that. If you know it's the cathode, you know it's reduction, you know it's gaining, you know it's positive. If you know it's the anode or you know it's oxidation, you know it's loss, you know the charge goes up, you know it's negative. All right, so you got to know all those things. So we will make a little chart of that. So one more thing you need to know about the anode and the cathode is, and the electrons flow alphabetically, anode to cathode, if that helps you to remember, or from oxidized to reduced, that's also alphabetical, or you know that this is loss and this is gain, so they must be going this way. Anyways, you gotta know which way the electrons flow. This one right here is gaining mass, this electrode, as we run the experiment, or the battery, and this one is losing mass. So this one gains mass. And you could also remember that, oh, reduction is gain, and this one loses mass. And I'll tell you why in a second. So sometimes people say the red fat cat because this one, as the reaction goes on, it gets fatter, like it gains mass. So what it's really going to look like is it'd be like an electrode that has like all this chunky stuff on it. So you might have seen an electrode that has like chunky film or like stuff formed on it, or you might see one that's kind of holy and falling apart. So this one is going to kind of look holy and falling apart, and this one's going to kind of have like extra stuff like stuck to it. It's going to have like all this residue on it because that's the one that gains mass. This one loses mass, it's going to have holes. The tricky thing is that people think like, oh, it gained electrons, so it gains mass. Okay, but we said electrons have like almost zero mass, so that's not actually why. The reason is, as these electrons come in, we fill, this beaker is filled with little ions that are like, ooh, electrons, and they come up to it. So let's say this is the electrode over here, just drawn bigger. They come up to it and they're like, ooh, and they stick to it because they're like, electrons, let's go up there. It's like an electron bar. So they come to it, they get themselves reduced because of the site of reduction, and they stick to it. So it's really not because it gains electrons, but it does. The reason is that those electrons then draw ions to stick to the electrode. This one, on the other hand, is losing electrons. So all the little pieces of metal, every time they lose an electron, they're like, I'm jumping ship. I'm going to jump into this water over here. Every time they lose an electron, that little piece of metal will like break away, and you end up having this like wholly corroded electrode. Whereas here you have like this filmy electrode with these things that have stuck to it because they're like, ooh la la, electrons. Okay, last thing I swear is this little connecting piece right here is what we call a salt bridge, and the notes are down there about salt bridge. So it's like, okay, why do you have this other connecting piece? Like, I know that the metals have to be far apart. I know they need to be connected by a wire because I want the electrons to go through a wire. But why have this extra little thing connecting them? And the reason is that if you kept sending electrons over to here, you would end up with all this like negative over here and all this positive over here, and then the electrons wouldn't flow in that way anymore because negative is not going to want to go towards negative. So you kind of like send negatives back through here and send positives back through here to like keep the charge evened out, so you don't end up with like one really negative end and one positive end, and then the electrons won't flow. So it kind of like keeps, they say it keeps charge from building up. But what people mistakenly say is like, oh, what flows through the salt bridge? Electrons. And that is not what flows through the salt bridge. I don't want my electrons flowing through the salt bridge. I want them going through the wire to power my device, right? Wires power things. I just want charged ions to go through the salt bridge to like settle out, even out my charge. I don't want electrons going through there. All right, so that's what it says here. What does a salt bridge do? It has ions flow through it to prevent buildup of charge. So electrons flow through the wire because you want electricity. Ions, which do also have a charge, flow through the salt bridge to prevent the buildup of charge. You could also, if you didn't have like two separate containers connected by salt bridge. I don't know if you can hear my son singing. It's really annoying. If you don't have them connect, two different containers with them connected by a salt bridge, you could have one container and have them separated by this little disc with pores. It's called a porous disc that lets the ions go through. All right. So once again, what this all does is basically you're taking oxidation and reduction. One loses, one gains electrons, and you're saying, let's force that flow of electrons through a wire to power a device. We have a name for each end, anode and cathode. You got to use these memory tricks to remember which is which. And you got to know that a salt bridge lets the ions flow back through, not the electrons, to prevent buildup of charge.